In the previous section, we used definite integrals to find the area between two curves. And now in this section, we're going to actually use definite integrals to find volumes of three-dimensional solids. So I'm going to show you in this section three methods that we can do this. There's a method called slicing, there is a method called discs, and then there's a method called washers. And each of these methods really depends on the solid. So you're going to have to evaluate the situation and determine which would be the best method to use. Now, first we're going to talk about the volumes and slicing method. So we have previously computed volumes of solids using geometric formulas. We have the formula of a cube, of a pyramid, of a cylinder, all kinds of things. Now, in this picture below, we have a picture of a cylinder. And we know the formula for that to find the volume of a cylinder. It's pi r squared h. And the reason why that's pi r squared h is because we take a cross section of that cylinder, which is a circle, and the area of that circle is pi r squared. Now, if I want to figure out the area over the entire height of the cylinder, if the height of the cylinder is h, to find the volume, then I have to multiply by h. And then in this picture, it shows that it's only doing it for above the x-axis. So if you wanted then to take half the cylinder, you could take 1/2 pi r squared h. So we have formulas for some of our basic volumes. But now if a solid doesn't have a constant cross-section and we don't have a geometrical formula for that volume, we can actually use the definite integral to calculate the volume of the solid using a similar method that we used when we found rectangles, and then we added up the area of each of the rectangles under the curve to approximate the area. So now we're going to do a similar method, but now we're going to find cross sections and slices that are three-dimensional and add up all the volumes of the slices. So if you see this abnormal shape here, what we're going to do is we're going to picture cutting it into slices. And when we cut it into slices, we can approximate each of those slices with the rectangular prism. We have the length, we have the width, and then we have the height. So we can find the cross-section area and then multiply it by the width to get the volume. So imagine that instead of doing rectangles now, we're making slices that are three-dimensional. So if you see this picture here, our endpoints that we're going to plug in to the area function is going to be x0, x1, x2, etc. And we're going to plug that in to get the height. Is I can estimate the volume. I can estimate the volume by figuring out the number of those rectangular prisms we have and creating a sum from 1 to n. If I multiply each of those areas at each of those endpoints and then multiply by the width of the area, we can get an approximation of that volume. But then if we take it further, just like we used to find the exact area, if I take the limit as n approached infinity, if I created more and more slices that are thinner and thinner and thinner, then I can get the exact area. So I can take the limit to infinity of the sum from 1 to n, using the area with the endpoints plugged in, multiply it by the width, and remember what that gives us. That gives us the definition of an integral, a definite integral. So whatever interval we're trying to do this on, we can find the exact volume by using the interval from A to B, taking a cross-section area and integrating that, and then evaluating it from A to B. So this is the slicing method. Now, if we come up towards the top, there's a basic problem-solving strategy for the slicing method. Step 1, you're going to examine the solid and determine the shape of the cross-section of the solid. It is often helpful to draw a picture if one is not provided. Part 2 says, once you determine the shape of the cross-section, then you're going to figure out a formula for that area of the cross-section. And then part 3, you're going to integrate that area formula over the interval to get the volume, which is exactly what we just discussed right here. Okay, let's actually apply this idea of slicing to show you how the formula was derived for the volume of a pyramid. So we know from geometry that the formula for a pyramid that has a square base is V equals 1/3 a squared h, where a is the side of the square base. And so now let's go ahead and use the slicing method to derive this formula. So if you look at this picture below, we have a pyramid with the square base, and it's orientated along the x-axis. So the point of the top of the pyramid is along the x-axis, and the x-axis comes through the bottom center of the square of the base. Now, if we take a cross-section of the pyramid, we know that that's a square. So we know that the area formula is going to be s squared for the cross-section. However, if we want to integrate this with respect to x, we need to do some kind of substitution for s and write it in terms of x. If we look at this second picture here, we see that we have similar triangles. And so I can write a proportion using similar triangles and write that s is to a and x is to h. And then when I solve that for s, I get ax over h. So now I have a formula written in terms of x. I can replace s with ax over h. So now I want to find the volume of the pyramid. And this is a general pyramid. We're looking for the general formula, not on a specific interval with numerical values. So we're going to start at 0. I'm going to label this in pink so it's easy to see. We're going to start at 0 and go along the x-axis. And my upper bound is going to be h, right? I'm going to go from 0 to h, because we're doing this in a generic format to find the formula for the pyramid. So I'm going to integrate this from 0 to h, and I want to integrate the area with respect to x. So now I'm going to plug in my area function that we found was ax squared over h squared, and I'm going to simplify this and square everything. I'll continue down here. Anything that's a constant, I'm going to pull out. So I have a squared over h squared, and I have x squared dx. Now, if I integrate this from 0 to h, I have my constant here pulled out. And when I find the antiderivative of x squared, I get x to the third over 3. Now, when I evaluate that, first I have to plug in h, so that gives me h cubed over 3 minus, now I plug in 0, so that gives me 0 cubed over 3. 0 cubed over 3, that's just 0. So what I'm left with is a squared times h cubed over h squared times 3. And when I cancel 2 h's on the top and the bottom, and I pull the 1/3 out in front, we have just derived the formula for the volume of a pyramid with a square base. Now we're going to talk about what's called solids of revolution. Now, a solid of revolution is when you have a region in the xy plane, and so you have some kind of function, we'll call it f of x, that's highlighted here in orange, that I just colored over in black, and then it's on an interval from, say, a to b, that creates a planar region. And then if you rotate that around the x-axis, slowly but surely it creates this solid, and this solid is called a solid of revolution. So in this next example, we're going to go over how we can find volumes by using the slicing method to find the volume of a solid of revolution. So we're going to use the graph f of x is equal to x squared minus 4x plus 5, and it's on the interval from 1 to 4. So this is going to be our planar region, and our function is going to be x squared minus 4x minus 5. Now, as we take that and we spin it around the x-axis, we're going to get this shape here that creates a solid. Now, since the solid was formed by revolving the region around the x-axis, if you notice, the cross sections are going to be circles. So if I take a slice in here, just pretend I take this slice right here, when I look at it, it's literally going to be a circle. Now the radius of the cross section, how far I come out, is going to be the value of the function. So using the slicing method, in order to find the volume of this, I know I'm going to do this over the interval from 1 to 4. And I need to evaluate the area of the cross section. Now we said that the area of the cross section is a circle that has a radius of the value of the function. The area of a circle is pi r squared. So that's going to be my area formula for the cross section. But I need to write this in terms of x, so I'm going to keep going. Since my r represents the value of the function, right, we set up here, then when I look at the radius, looking at it here, that's the value of the function. So I'm going to plug in the function for r. So I have pi, and then in for r, I'm going to put x squared minus 4x plus 5, and that's going to be squared. Now to finish this up, my pi is a constant, so I can pull that out in front. We're going to square x squared minus 4x plus 5. So I got to square that first. I'll let you guys do that on your own, but what you should get when you're done is x to the 4th minus 8x to the 3rd plus 26x squared minus 40x plus 25. Now I can find the antiderivative and evaluate it from 1 to 4. So let's see, the antiderivative of x to the 4th is x to the 5th over 5. The antiderivative of 8x to the 3rd is going to be 8x to the 4th over 4. The antiderivative of 26x squared is going to be 26x to the 3rd divided by 3. The antiderivative for negative 40x is negative 40x squared over 2. And then the antiderivative for 25 is 25x. Now I got to evaluate that from 1 to 4. Again, since we're getting better and better at this, I'm going to let you do that. Don't forget that you have a pi in front here. So whatever you get when you evaluate this from 1 to 4, don't forget to multiply it by pi. But what you should end up getting is 78 over 5 pi. And then, of course, if you want, you can put that in terms of a decimal, but then that would be an approximation. This is the exact value. Now, for those of you who are very visual like I am, and I really need to see the picture to comprehend and really understand what's going on, there is a really cool tool online that's free and it's called GeoGebra. And if you're not given the picture for your homework or the picture in the textbook while you're reading, sometimes it's hard for us to visualize what that solid of revolution is going to look like. So I'm going to show you how you can use this online tool that you can actually spin the function around the x-axis. And if you go to geogebra.org and you click on the button that says calculator, or you can actually just go right to geogebra.org/calculator, and it's going to bring you up a free online graphing calculator. Now, the neat thing about this is we can do three-dimensional stuff in this one online. So what I want to do is show you how you can use this free tool that's online to help you visualize these solids that we're trying to find the volumes of. A lot of times it's easier to figure out what formula you need to know if you can visualize that solid. So what we're going to do first, when you go to the homepage for a GeoGebra calculator, since we're going to be doing three-dimensional stuff, the first thing you should do is switch your graphing calculator mode up here using the drop-down menu and go to 3D calculator. Now you'll see that your graph is now changed to 3D. So the y-axis is the green axis. The red axis is the x-axis, and now we have a new axis that makes it three-dimensional that comes up through the page, which is the blue axis, which is now z. So let's go ahead and define our function. So we were using the function f of x is equal to x squared minus 4x plus 5. Now, when I hit enter, this is going to show up on my green and red axis on that flat plane because this function is not three-dimensional. So it's going to look like a parabola on the green and the red plane. So there we go. Now, if you want to change the color of that, you can go to settings, and there's all kinds of stuff that you can do here. You can choose color if you want to change the color. I like doing my graphs in black. You can change the line thickness. You can make it a dashed line. There's all kinds of things you can do to adjust your graph. I'm going to create a slider because I'm going to show you how we can take this parabola and rotate it around the x-axis to get a visualization of what that solid would look like. So the next step is to type in here A and then hit enter, and it's going to create an automatic slider for you. Now, you're going to want to adjust the maxes and mins for that slider. So to do that, you're going to go to settings on the slider. And since we want to rotate this around 360 degrees, I'm going to go to slider here. And I want to tell it that I want to start at 0 degrees and I want to rotate it a max of 360 degrees. Now you have to put in DEG, so then it will translate it for you to ratings, or you can figure out what the ratings are and put it in directly. Now when I hit enter and I exit out, now it's set up so when I slide it, it's 0 to 6.28 ratings, which is 2 times pi, right? Approximating 6.28. Now, the last thing I want to do to see this thing rotate is I'm going to put in a command called surface. And you want to click this one here that says surface, and then you put in the curve, the angle, and the line. So the curve tells you what you want to rotate. The angle tells you how far you want to rotate it. And the line tells you what are you going to use for your axis when you rotate it. So I'm going to choose that option. And then for my curve, I'm going to put in f, because we defined our function up above as f of x. Now, if I defined it as g or something else, I want to make sure that I label it correctly. For my angle, we are going to use the slider so that we can slide it and angle it the way we want to. So I'm going to put lowercase a in there. That's the name of my slider. And then for my line, I want to rotate this around the x-axis. So I'm going to write x. Now, for the command for the x and the y-axis, you have to have capital letter on the A for the axis. So it should look like this. So X, no spaces, and then capital A axis. Now, when I hit enter, we should be ready to go. So now I'm going to use my slider and I'm going to slowly slide my slider, and it's going to show me what the shape looks like as we rotate it around the x-axis so that we can get a good visual picture of what that looks like. Another really cool aspect of this is that you can actually grab the graph and like rotate it around so you can look at it from all different angles. So you can see what that looks like when you click and drag it. Okay, now the other neat thing is if I want to see what this looks like rotated around the y-axis, I can just go up here, edit, and change X to Y, and then hit enter. And then when I use my slider, it's going to rotate it around the y-axis, and I'm going to get a completely different shape. So now it's rotating around the green axis, and I'm going to get what looks like a bowl shape. And then again, I can click and drag on it to see what it looks like from different directions. One last thing I want to show you, if there's a picture that you want to save so that you can refer to it later, you can come over here to these three lines, open the menu, and you can click save so you can save your work that you've done in here, or you can export the image and save it as, I think it's a PNG. Let's try it and see what happens. Export image, and then I can download it. Yep, it's saved as a PNG image. So you can actually export your pictures as well if you want to save them. Now, if you do want to save it, make sure that you have it in the position you want before you save it, because it will save it exactly how it shows on the picture or on the graph when you hit save. So this is a really neat tool that you can use to visualize these solids if you're not given the picture in the book or in your homework. Now, when we use the slicing method, like what we just did with a solid of revolution, a lot of times that's called the disk method, because when you rotate that function around the axis, it creates cross sections that are circles. And then you take those slivers of circles, and they're really like the volume of a disk. The general rule for the disk method is you just integrate over the interval of interest. You use your function as the radius, because that's how far your disk is going to go, and then you multiply it by pi. So you have pi r squared dx, and your r is going to be written in terms of x when you plug in your function. So let's look at this example. We're going to use the disk method to find the volume of a solid of revolution, and this is the first example. We have two of them. It says use the disk method to find the volume of the solid of revolution generated by rotating the region between the graph of square root of x and the x-axis, and we're going to do this over the interval from 1 to 4. So when we look at picture A, we're looking at the interval from 1 to 4, and we create this planar region. And then when we spin it around, we get this solid. And when we do that, our cross sections are going to be circles that have a radius of square root of x, because that's how far, if I look at this picture, that's how far my radius is. It comes out to the function, which is the square root of x. So to find this volume, I'm going to set up an integral from 1 to 4, and we're going to do pi r squared. That's our area. So we're integrating the area to get the volume. And since I want to make sure I rewrite it in terms of x, and we know my radius is the square root of x, I'm going to rewrite it like this. So when I simplify this, I get pi, and then the square root of x squared is just x dx. I can pull my constant out and integrate x dx. And when I do that, I'm going to find the antiderivative of x, which is x squared over 2. And I'm going to evaluate that from 1 to 4. So I'm going to plug in 4 first. When I plug in 4, I get 8, because 4 squared is 16, and 16 divided by 2 is 8. Then I'm going to plug in 1, and I get 1/2. So I get 8 minus 1/2, which is 15 over 2 pi. And then, of course, you can put it in terms of a decimal if you'd like. Now, remember that we're doing volume here. So if I want to write units in a generic way, I got to keep in mind that this is going to be units cubed now because we're doing volumes. Algebra, and see what this looks like when we rotate it around the x-axis. We already have seen a picture of it because the book provided one, but it's nice to practice. I want to stress that this is not required for you to know how to do this for the class. It's just an extra helpful tool for you to have. So since we're going to be doing a 3D graph, I want to make sure I change my graphing mode to 3D. That's always the first step. Then I'm going to define my function. It's going to be defined in 2 dimensions. So it's going to show up on the green and the red axes flat on that plane. And to get the square root function, I have a keypad down here in the left-hand corner. I can click on that icon and my keypad will open up. And I can choose the square root. And then I can put in x. So you can see that my square root function just popped up here on the graph. If you want to adjust it in any way, you can adjust the axes, you can adjust the color. Let's do blue for rogues. The next thing we need to do is I'm going to define my slider. So I'm just going to hit A and enter, and my slider will pop up. And then I want to make sure I go to settings on my slider and tell it on the slider tab. I want to tell it that I want to go from 0 to 360 degrees. So I want it to be able to completely rotate one rotation around the x-axis. Then I'm going to hit enter. Now my last thing that I'm going to do is I'm going to define my surface. So I'm going to pull up my surface command, and I always want to choose this one that says curve angle line. I'm going to hit enter. For my curve, I'm using the function square root of x. So I'm going to define that as f. For my angle, I'm using the slider because I'm going to use that to spin it around. So I'm going to hit A for that. And then for my line, I'm going to choose either the x-axis or the y-axis. Now, since we're spinning it around the x-axis, I'm going to choose x-axis. So you're going to choose either lowercase x or y, depending on which axis you're going to use, and then capital A, X, I, S. When I hit enter, it's going to be ready to go. So I'm going to start at 0 degrees on my slider, and I'm going to slowly rotate this around. Just use my slider and grab it and pull it around, and you can see what that solid will look like once it completely makes a full rotation. And then, of course, I can look at it from all different directions if I want to click and grab on it. So far, our examples have all been about regions that are revolved around the x-axis, but we can also generate a solid of revolution by spinning it around the y-axis as well. And so all we need to do to set that up is to write everything in terms of y instead of x, and make the function that's written as x in terms of y the radius. So now let's look at this example. It says let R be the region bounded by the graph g of y is equal to the square root of 4 minus y and the y-axis over the y-axis. And it's going to be on the interval from 0 to 4. Just keep in mind this is on the y-axis. Sometimes it's hard to change our mindset. We're going to use the disk method to find the volume of the solid that's generated by rotating r around the y-axis. So this function, x equals the square root of 4 minus y, really is the function 4 minus x squared is equal to y, but it was rewritten in a way that it was set equal to x instead of y, so it's in terms of y. This is a quadratic, and since we're only looking at the positive square root, we're looking at this side of the quadratic. Now, if the function said x is equal to negative square root of 4 minus y, we would be looking at this side. So just a quick review of algebra, so we know where this is coming from. When we spin this around the y-axis, we're creating a disk, and the radius of that disk is going to be the function square root of 4 minus y. So we're going to set up our integral, and if we look at this, if we were doing it in terms of x, our interval would be from 0 to 2, but because we're doing this on the y-axis, our interval is going to be from 0 to 4. So we're going to set this up as 0 to 4 of pi r squared dy. And I'm going to replace my radius with my function. So I have the square root of 4 minus y squared dy. Now I can pull the pi out in front and simplify the square root of 4 minus y squared. That would be just 4 minus y dy. Now when I find the antiderivative of that, we're going to get 4y minus y squared over 2, and we're going to evaluate that from 0 to 4. When I evaluate that and I plug in 4 first, I'm going to get 16 minus 8. And then when I plug in 0, I'm going to get 0. And so inside the brackets, I'm going to have 8. And then I still have to multiply that by pi. So my final answer is going to be 8 pi. So now let's see what this looks like. Now, since GeoGebra likes things that are in terms of x, I rewrote the function like I showed you when it was in terms of x. And I'm telling GeoGebra to only graph the positive side of that. So I'm telling it to graph from x is greater than or equal to 0. So we get our parabola that's only greater than 0. And then I'm just using my slider from before, and I just redefined my function. And I want to make sure that since we're rotating this around the y-axis, that it says for my line portion of the command that it says y-axis with the capital A. And now, when I use my slider, we can see what it looks like when it rotates around the y-axis. And this is the picture that's shown in the book, but it's fun to practice and to get a hands-on look at what that looks like as it starts to rotate and create that solid. So now let's talk about the washer method. Sometimes a solid of revolution can have cavities where they're not completely solid all the way through. And this is sometimes just the result of the way that the region of revolution is shaped with respect to the axis of revolution. So some other reasons that it could cause a cavity, it could happen when the region of revolution is defined by the region between two functions. And another way that it could happen is if you are revolving it around a line that is not the x or y axis. For example, I might revolve something around the line x is equal to 5. There are different reasons for why when you take a solid and you revolve it around an axis, that you might have a cavity. But when that happens and it's not completely solid, you want to use what's called the washer method. And so here's an example of what that might look like. If you are taking this function, we're looking at this picture right here, picture A. If you look at the graph of f of x is equal to square root of x, and then you look at just the horizontal line, y is equal to 1, and you find that area between the two graphs, and then you revolve that around the x-axis, rather than get a solid disk that is a complete circle for a cross-section, but you're going to get a washer. It's going to look like a donut with a hole in the middle. So it's not a disk, it's a washer. So in order to find the area of that washer, your radius is going to be the difference between these two circles. So I'm going to highlight the outer circle in pink, and that's going to be what's created by the function square root of x in this example. And then if I take blue and highlight this middle circle, that's going to be created by the line y is equal to 1. The radius of the washer is going to be the difference in the radiuses of those two circles. So now when we use the washer method, we're still going to find the volume by integrating the area. However, that area is going to be defined slightly differently now because it's the difference between two circles. If we got a washer, this area is going to be the area of the outer circle, I'll label it AO, minus the area of the inner circle, I'll label that AI. So if I have an outer circle, that's going to have a different radius, minus the area of the inner circle, that's going to have a different radius. When I factor out the pi, I got the radius of the outer circle minus the radius of the inner circle. And since the radius is being represented by functions, that's going to be f of x squared minus g of x squared if f is the outer function and g is the inner function. And that's exactly what we're doing in this formula here. So let's go ahead and look at this example of using the washer method. So we have the line y equals x, and then we have the function 1 over x. So the function x is in blue and the function 1 over x is in orange. So we're looking at this area here, this region, and when we rotate that around the x-axis, we get a disk shape, but because of the function 1 over x in the center, we're going to have this empty hole in the middle. So when we take a cross section, the outer circle is going to be created by the function f of x is equal to x, and the inner circle is going to be created by g of x is equal to 1 over x. So when we set up our integral following this rule up here in the box to find the volume, we're going to integrate over the interval from 1 to 4 in this case, because our interval, if you notice up here in the graph, is from 1 to 4. Then we're going to take pi times f of x squared minus g of x squared. It's going to be the difference in the radius for those two functions to create that hole. And then this is in terms of x, so we're going to write our dx. So I'm going to take x squared, f of x is my x, g of x is 1 over x, and I'm going to square that. When I find the antiderivative of x squared, I'm going to get x to the third over 3. When I find the antiderivative of 1 over x squared, I get a double negative, which changes this to a plus. And then I get 1 over x, and I'm going to evaluate that from 1 to 4. When I evaluate that from 1 to 4, I'll let you practice doing that, but you should get 81 pi over 4. Don't forget that you have this pi out in front, so whatever you get when you evaluate inside the brackets from 1 to 4, don't forget you have to multiply that by pi. Now, just like with the disk method, we can also apply the washer method to solids of revolution that result from revolving a region around the y-axis. So all you would do is just follow the same rule, but you would write everything in terms of y. And here's the rule right here. Now, rather than walking through an example of a washer method revolving around a y-axis, we're going to actually go into an example that's a little bit more tricky and consider a case where you're revolving the solid around something other than one of the major axes. We're going to actually walk through an example of where you have to imagine that you're revolving this region around the line y equals -2. So there's a shift. And when there's this kind of a shift, you really have to understand what the picture looks like and really focus on that cross-section to understand how you have to set up your radius. So looking at this, our region that we're going to revolve around the line y equals -2 is going to be this area that's bounded by the line 4 minus x and the x-axis. So this is what's going to spin around the line y equals -2. Now, when we do that and it spins, we're going to get it so that it comes down like this, and it's going to spin around. And this that I'm shading here in purple is actually going to be the center of that washer where you're going to have that cavity, that empty space. You're going to have this. I'm trying really hard to draw this well, but then you'll have the region on this other side. So it's going to come around like this, and this will be your open circle. So when we look at a cross section and we look at the washer, the center is going to be around the line y is equal to -2, and there's blank space of a radius of 2. It comes out, let me do green for this. From this line, y equals -2, it comes out this way 2 and this way 2. My radius of that inner circle is going to be 2. If we look at the center, where you have y equals 2, that radius from the entire center out, that's going to be the function 4 minus x, but you're going to have an extra 2 that you have to count because it's shifted down 2. Here's the x-axis. It's shifted down an extra 2 spots. So we have to add 2 to the length of that radius. And this is why it's tricky, and you really have to understand the picture. So we're going to add 2 to that function to get our radius. So the radius from the center all the way out is going to be f of x plus 2, which is 4 minus x plus 2, which would give us 6 minus x. So when we set up our integral, we're going to go from 0 to 4, and we have pi times our outer radius squared minus our inner radius squared. And we set our outer radius was 6 minus x squared. And our inner radius was 2, so we're going to square that. When we square 6 minus x and we subtract 4, we're going to get x squared minus 12x plus 32 dx. Now I'm going to find the antiderivative. So I have x to the third over 3 minus 12x squared over 2 plus 32x, and I'm going to evaluate that from 0 to 4. When you complete that and you remember to multiply whatever you get inside the brackets times pi, don't forget you have a pi out here, you should get that your final answer is 160 pi over 3. And because this is a volume, we're going to label this generically as Unix cubed.